Hello again. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host. I hope you're well. In this episode, it's episode 370, so it's all dedicated to audience questions. And this is where we turn it over to the people who listen to us. And they basically throw questions at us and we pretend we know what we're talking about. And we're going to be talking about the gravity map. And a few thoughts from Eric on what that might mean for his home country. Also, questions about light, space-time. That one comes up never. Black holes, even less. Gravity is becoming a common theme from the audience. So we'll tackle a couple of different elements of gravity, and we'll also tackle elements and much, much more coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you this fine day?
I am quite well, sir. And what about you? All good?
Yeah, all good, thanks. Yeah, It is. It's a lovely sunny day here in Sydney. It looks like spring has arrived, which is a bit early, really. Well, actually, it's only 2 days early, isn't it?
Yes. Well, I think it's come here much, much earlier than normal. We usually have fairly cold weather, sometimes into late September.
Yeah,
we've been getting, late August and into September, some pretty big numbers on the thermometer, numbers that you don't usually see around that time of year. So certainly spring broke through real quick this year, which I don't mind. I prefer the warm weather, must say, but I live with people who prefer cold weather, so I can't win. I can't win that argument.
No.
But it's my time to shine for the next 6 months, so that'll be good.
There you go.
Shall we get into the audience questions, Fred?
There's probably nothing else to do, so we might as well. Yes, yeah.
Okay, let's jump on the first one. This comes from Eric.
Hello, Andrew and Fred. My name is Arul Krishnamurthy. I'm recording this message from Edinburgh in Scotland. The question I have is the GOCE gravity map that I came across a couple of years ago. As per this GOCE gravity map, gravity is not uniform across the globe. It is higher in some places, it is lower in some places. What I'm interested is in this GOCE gravity map, the southern part of India, where I'm originally from, is the lowest gravity levels in the whole globe. I want to understand the relationship between the gravity levels mapped by GOCE and escape velocity. Does the low levels of GOCE mapping means if there is a launch from there, does it need a lower fuel because the escape velocity will be lower? Thank you very much. I'm a regular listener of your show. Both of you are doing a wonderful job. I like your show. Thank you.
Thank you. I hope I've got your name right, Eric. I think I picked that up, but I might be wrong and I apologise. But yes, and that Scottish accent was absolutely thick and fast there, I reckon. No, he's in Edinburgh now, but hails from India. And you know about the gravity map, Fred, and I think they've updated it because we both thought before we started the show that Australia was the part of the world with the lowest gravity measures, but that's no longer the case. Maybe.
That's right. And that highlights one of the aspects of what we're talking about here, which is that the gravity as measured from space, looking down, mapping the differences in gravity across the Earth's surface, they change with time. So it's not, necessarily related to where a country is or where mountains are or things of that sort. It may well be more to do with what's going on under the ground. So now what our listener referred to, and delighted he's in Edinburgh, as one of my favourite cities in the world, having lived there for a long time, is the GOCE data. That mission is a European Space Agency mission, and it's once again a gravitational sampling mission. The one that I thought was going to come our way in this question was an earlier one, which is a NASA mission called GRACE. GRACE was the Gravity Recovery and Climate Experiment. And GRACE has got actually nicer animations on its website than GOCE. But they tell the same story. So what we're looking at here is basically a map of variations in gravity across the Earth's surface, and that variation is it's corrected for the slight variation you get because of the Earth's rotation. Because at the equator, you're very, very slightly lighter than you are at the pole in terms of your weight. So it deals with all that. And what we wind up with is a map of what's called a gravity anomaly. In other words, a map of where things are different from the average. If I can put it that way, that's the bottom line there. So the gravity anomaly is essentially, as I said, it's the variation of that parameter over space. I'm desperately looking, as you can probably tell, Andrew, for a scale on the gravity anomaly diagrams, because they're very, very small anomalies that we're measuring. So I think the numbers are in thousandths of the constant of gravitational attraction, and they vary by very small numbers. So these variations are only slight compared with the overall gravitational pull of the Earth. So you're not going to feel anything different. There are certainly, when you look at the detailed gravitational maps, and certainly GRACE, which is just the one that I'm finding easiest to access at the moment, they do tell you about mountains on Earth. A lot of the mountainous regions of the Earth, like the Andes, like the Himalayas, have a strongly positive gravitational anomaly. And that figures because those mountains are quite dense and you're flying over a more dense region of the Earth's surface. But some of these variations are much more subtle and come about because of ocean currents. And that's why the spacecraft, this particular one, was called Gravity Recovery and Climate Experiment, because it's all about how things like ice masses, ocean currents from those ice masses, how they flow, if they're melting, all of those things can be picked up by looking at these gravitational anomalies, which tells you how sensitive the instrument is. But I think there are also possibly things that are related to the internal structure of the Earth, because we've got, not far below the surface, we've got this semi-fluid region called the mantle, which is where the magma comes from that boils out into volcanoes. And that stuff's moving around. It's kind of sloshing around as the Earth rotates.
Yes.
And so you would expect higher and lower regions of density to move with respect to the Earth. And that's what the gravity animations show, that there is movement. Some of it comes from things like ocean currents, but some of it probably comes from deeper layers. Now, our listener is absolutely right. There's a low area to the south of India, and that may well be related to things happening underneath the crust. Just coming to the the question though, at the end of that lovely audio, it's not likely to make enough of a difference if you've got a low gravity region to the escape velocity of Earth in that point, because it's such a tiny difference from the overall gravitational pull of the Earth. What makes a much bigger difference, and once again, that's appropriate for the south of India. The nearer the equator you are, the more of a push you get by the Earth's rotation to get yourself into space.
Bit of a slingshot.
Your slingshot, exactly. That's right. Yeah. As the Earth's rotating, it gives you an extra about 0.5 kilometre per second on the equator, which, given that you need to get horizontal velocity. Sorry, I've moved my screen there. You need to get horizontal velocity of nearly 8 kilometres per second to go into orbit. If you can get a free 0.5 kilometre per second, you're actually winning. It saves you rocket fuel.
Yes, indeed.
Yeah.
So the gravity effect, probably not an advantage, but being closer to the equator is the bonus.
That's correct.
It's interesting looking at the map. It's definitely a very big blob of lower gravity over the Indian peninsula, if you like, but down into the Indian Ocean, that area, and leaking down towards southwestern Australia. But there's also some low gravity pockets on the east and west coast of North America, and the tip of South America, and up into Asia as well, so north of India, and down around Antarctica, which is fascinating. So there's and the places where there's the highest amount of gravity, northern Australia, New Guinea, up into some of those Asian countries, and up around, where am I looking? Middle East, up around the Middle East and Europe.
Yeah. But, this is the thing, like this, the middle of the North Atlantic Ocean's got a high gravitational pull as well. And that, you'd intuitively think that if it was to do with the thickness of the Earth's crust, the crust is thinner in the oceans. And yes, that might account for the low gravity in the Indian Ocean there, but the middle of the Atlantic's much, much higher. So again, it speaks of things going on beneath the surface, I think.
Oh, okay. Thank you for your question. Makes for an interesting discussion. Gravity is something that we sort of understand in pockets, boom, boom, but overall we still really have a lot to learn about it.
Yeah.
Now, let's move on to... Thanks, Eric. Let's move on to our next question from Buddy.
Hello, Space. That's Buddy from Oregon again. Here's a quick one. Can light stand still? If it does get stopped, what happens to it? When a black hole absorbs light, does it gain mass? Thanks, guys. Keep up the good work.
He's a real thinker, Buddy. He comes up with some interesting concepts from time to time. Can light stand still? I think the answer is yes. They did an experiment not so long ago that we talked about, and they did actually manage to stop a photon, did they not?
Yes, that's correct. I don't know the details of it, but you're right. Light has been shown to be stationary, and I don't know too much about the physics that lets you do that. The normal process of refraction, as light passes from a less dense medium to a higher density medium, that slows down the speed of light. It's slower in water than it is in air, and it's also slower in glass than it is in air, and that's why you get the phenomenon of refraction. It's how we make lenses work, because of the speed of light slowing down in a medium. But I think the techniques used to stop light are quite different. Light stops when it hits a surface.
Hey, I was going to say, it's like when you hit a tennis ball, it stops fractionally before it bounces in the opposite direction.
Yeah, what I was going to say, certainly in the case of light hitting an opaque surface, then it's being absorbed, so the light does stop. But
yes,
at the same time, it ceases to exist. It stops being a photon anymore. But these experiments showed that you could actually stop a photon and then let it go again. I should check up on that stuff. It's quite neat physics, which certainly has applications in some of the more esoteric sorts of experiments that I think people are doing in physics laboratories, not like the ones I did in my physics laboratory at school, where he stops things, usually bits of paper, as they flew across the room, being aimed at by another fellow student. So to the other part of Buddy's question, does light increase the mass of black holes? I guess the answer is yes, because light is energy, and so if you've got photons being absorbed by a black hole, then in some small way its mass must increase.
Okay.
I stand to be possibly corrected on that.
Yeah, well, it's one of those things, isn't it? But the answers to your questions, Buddy, at this point are yes and possibly yes. We can say, but yes, you can stop light. They have actually done it in a lab, I believe. If you do a bit of a web search, you might be able to find information about that, because it was a very recent experiment that they've released a paper on. Thank you, Buddy. Let's go to Neil in Melbourne. He says there's been talk recently about the energy that causes the universe to expand coming from black holes. If this is so, then wouldn't we see the space-time around or near a black hole expanding at a faster rate than that further away from the black holes, for example, between galaxies? Or is that in the spaces between the filaments of the cosmic web? Wouldn't the filaments of the cosmic web be expanding faster?
And that's a great question. So I have to say, excuse me, we did cover this story a few weeks ago, that there was some evidence that black holes were the source of dark energy.
Yeah.
Now, I did understand it when I read the paper, I think, but I can't remember what the details were. And it was one that seemed to, what was the story? It seemed to be something that would be not in the way that Neil is suggesting, limited to the immediate vicinity of black holes. I'm trying to remember the terminology. I haven't really got time to look it up now, but certainly the idea was that what a black hole does actually affects the whole universe, so that you're not just increasing the dark energy around a black hole, and therefore making it lumpy, if I can put it that way, because we think dark energy is the same everywhere. That's the that's the current thinking, and so for that theory to hold water, there must be a way in which it can account for that. And I'm sorry, it was probably a couple of months ago, or rather more than that we looked at this, and I did look at the mechanics. And yes, I was convinced at the time that might be the source of it, but I'm afraid I can't grab it from the depths of my mind at the moment.
Okay.
Maybe we should revisit that.
Possibly so, because it is really, it was a really...
it's fascinating.
Significant, and a fairly significant claim that may hold water. You don't know, because there's so many unknowns around dark energy, black holes, and dark matter. We just know all these things exist, that maybe they coexist, maybe they rely on each other. We haven't quite put the pieces together, but we're chipping away at it, I suppose. That would be the best way to describe it. Maybe. I don't know.
Chipping away, yeah.
About all you can say.
There must be a dad joke in there, but I can't grab it at the moment.
Possibly so. So, Neil, we'll get back to you. Watch this space. There you go. There's the dad joke.
Thanks.
You wanted it.
Yeah.
You're regretting it now. Thanks, Neil.
I'm just looking at the article in Physics World about the about the linking, and it is it's to do with the idea that maybe black holes aren't singularities, This is Physics World, I'm quoting. Most models of black holes suggest that at their heart is a singularity, a point at which mass is squeezed into an infinitesimally small point and thus becomes infinitely dense. The new cosmological coupling replaces this singularity with vacuum energy, proposed as the source of dark energy.
Ah.
That was the thing that I was trying to get my head around. It's a coupling issue, cosmological coupling. That was the bottom line. Now, there's a lot of text here which I haven't time to read now, but that I think is the heart of the matter.
Okay. Very good. All right. Thank you, Neil. Great to hear from you. This we'll probably talk about it more. It's one of those areas that seems to keep spawning interest and questions. So I don't doubt we'll get some more questions as a result of your question, Neil. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Did you miss your deadline to renew your Medicaid coverage? You can still send your completed annual review form to Healthy Connections Medicaid. You may be assigned to another health plan, but you can ask to come back to First Choice within 60 days of renewed Medicaid eligibility. It's your family. It's your choice. First Choice is the right choice. Renew and choose us. Visit selecthealthofsc.com/renew to learn more.
When you visit Arizona, time is measured in moments, not minutes. Like the moment your work stress disappears as you kayak through the canyons. Or the moment you discover the life-changing effects of prickly pear chocolate. But nothing beats the moment you see the Grand Canyon for the very first time. Visit a new state of mind. Learn more at hereyouareaz.com.
Roger, you're loud and clear here also.
Space Nuts.
Okay, Fred, let's move to our next question from Ulla.
Hello, guys. Ulla here from Sweden. Thank you, guys, for an awesome podcast. I just discovered it a couple of weeks ago and I'm hooked. I have a question regarding black holes and charge. As we all know, black holes squeeze things down to very, very small sizes, like into a form of matter we don't understand even, like a point-like mass. Then how can it be that if an electron enters the event horizon and gets squashed down to basically nothing, how can that leave an electrical charge when the actual electron is destroyed? Wouldn't the charge be destroyed along with it? That's my question. So thank you very much again, guys.
Okay, thanks, Ulla. So the question basically is an electron gets dragged into a black hole and spaghettified or squashed or whatever. What happens to the charge?
So there is I'm just reading about charged black holes here.
Oh, okay.
That's really, really interesting. And it sounds as though the charge is not destroyed.
Oh.
Because the sentence I'm reading here, which comes from Wikipedia, charged black holes, since the electromagnetic repulsion in compressing an electrically charged mass is dramatically greater than the gravitational attraction by about 40 orders of magnitude, it is not expected that black holes with a significant electric charge will be formed in nature. So, make of that what you will.
I'm trying to. You're getting into the realm of I haven't got a clue what you're talking about.
Yeah, well, that's right. So, Ulla's question is great. If an electron drops into a black hole, what happens to that negative charge that it's got? And what this is suggesting is that actually it's suggesting it wouldn't be preserved, I think.
Oh, okay.
Let me read that again. The electromagnetic repulsion in compressing an electrically charged mass is dramatically greater than the gravitational attraction. So I think what it's saying is that would not contribute to the charge of the black hole. So you don't get a significantly charged black hole in nature. There are a category of charged black holes that exist in theory. In fact, just to go through a quick itinerary of types of black holes, the Schwarzschild black hole, which is Schwarzschild was the physicist who in 1915 solved Einstein's equations of relativity to basically calculate what a black hole would look like, and then promptly died on the Eastern Front in the First World War, actually of an illness, not of injuries. Schwarzschild black hole has no rotation, angular momentum, and no charge, so that's a kind of clean one. A Kerr black hole, KERR, has angular momentum or rotation, but no charge. A Reissner-Nordstrom black hole has no angular momentum, does have electrical charge. And a Kerr-Newman black hole has both angular momentum and an electrical charge. And I think the suggestion here is that the latter two don't exist in nature.
Oh, okay.
I think we've wandered off the question a bit here, still. Andrew. But well, as always, we're learning a lot on these things.
Yes, we are. The curiosity of our audience spawns all sorts of interesting discussions, I think.
Yeah, I'll try and find out a bit more clearly what happens to an electron if it falls into a black hole.
Okay. Thanks, Ula. Lovely to hear from you, and glad you love the podcast, and welcome aboard. Let's get a question from Missouri. Michael says, hello, Andrew and Fred. I've been crazy about space stuff since I was a kid, and some would say I'm even a space nut. I've been listening to your podcast for the last 4 months and have run out of episodes already.
Wow.
Seriously, wow. Love the show. My question to Professor Watson is about gravity. How far away does gravity affect objects in space? I know everything in the solar system tugs at each other, like the sun pulling on Jupiter and even Pluto pulling on the sun slightly. But how far does that reach? Does Pluto pull on Alpha Centauri's system? What about a galaxy 5 billion light years away? Does that very distant galaxy pull on us? Just how far does the effect of gravity actually reach? Thank you. Can't wait to hear the answer to this. Yeah, we don't know.
Well, we do, actually.
I figured you would. That's one I thought we would know.
Yeah. So it goes on forever. It's sort of infinite. Now, having said that, because if we can turn it into a force, it's not actually a force, it's a distortion of space, but thinking of it as a force for a moment, it's an inverse square law that relates to that force. So if you stand twice as far away from a gravitating object as you were before, you'd feel 4 times the less gravity, because it's the square, 1 over the square of the distance is the strength of the gravity. It's related to that. In fact, that's Newton's law of gravity. Gm1 m2 over r squared. Gravitational constant times the product of the two masses over the square of the distance between them. So the further apart things are, the weaker the gravity gets. And it gets weaker very quickly because it's this square relationship. It's not just going up linearly. And what that means is that it doesn't take very far for you not to be able to feel it, but it's still there. The effect is actually one that there is gravity there from. So you're talking about Pluto and Alpha Centauri. At the distance of Alpha Centauri, Pluto does exert a gravitational pull, but it is so minute that it's completely swamped out by much more local masses. More local objects.
Okay. No, that's fascinating. I didn't realise that something as small as Pluto could have an effect on something.
Yeah, it doesn't have any real effect,
but it's there.
But theoretically, that's right. It does. Yeah.
This is one of my lame examples. You're standing on the beach and you get hit by a wave, you feel its effect. But if you're in the middle of the ocean and a wave of similar power sweeps through you, you don't really feel it because you're not at the impact point. I don't know.
Yeah.
A vain attempt to understand.
I think, yes, yeah. I think you're talking about, wave motion itself is a really interesting thing. And we know that gravitational waves exist. So there's gravity comes in waves as well. So there's some merit to your analogy there, Andrew.
Yeah. Just a little bit loopy. Okay. Thanks, Michael. And to you also, welcome aboard. I'm glad you're enjoying the show. Cramming 370-odd episodes into 4 months, that's dedication. We should give you a badge. But thanks for sending us your question. Dermot in Sydney says, Dear Andrew and Fred, to create the range of elements we find today on Earth and within our solar system, everything from hydrogen to uranium, required the fusion energy of stellar nurseries, merging white dwarfs, and a massive supernova, according to my research, he says. What are the latest theories on how many times our elements have been reworked and recycled, or how many sources did this matter come from before it coalesced to form our solar system? Beloved planet Earth, and in turn, you and me. Regards, Dermot.
Yeah, I like that.
Lots.
The lots is the answer, actually, because you can't really... what you can do, and I guess what astronomers do, is assume a fairly constant rate of stars being born and dying and all the other stuff happening, the things that Dermot mentions as producing the higher order elements, the more massive elements. Remembering that I think in the inside of normal stars, you can only form elements up to iron in the periodic table. And to go beyond that, you need much more high energy processes like supernova explosions, like colliding neutron stars. Those are the ones that produce the higher order elements, the higher ones in the periodic table. So if you take a world like ours, or a solar system like ours, and look at the relative abundances of all those elements, what it's telling you is it's telling you that these processes have happened, and in a way it's measuring how long they've happened for, rather than how many individual explosions, how many individual supernovae, how many individual dying stars need to have gone through it. So you assume a kind of production rate of the elements from these various processes. And in fact, what I'm trying to do is turn the argument on its head, because this is the way we use to measure the ages of stars, basically. You look at the relative abundances of the elements within the atmosphere of a star, and it gives you a measure which is fairly complicated because stars are different. They've got, different characteristics, but it in general gives you a measure of the age of a star. So the fewer elements that are in it, the earlier that star formed in the history of the universe. So all this churning's going on. The elements are being produced by all these different processes. And so as time goes on, new stars have richer and richer atmospheres in terms of the abundance of the heavier elements.
Okay. Wow. All right. There you are, Dermot. Good question. We're getting some great questions today.
That's right.
All right. This is Space Nuts. Andrew Dunkley here. Fred Watson there.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
3, 2, 1.
Space Nuts.
To our next question, Fred, this is a real quick one, and we don't have a name, but you'll have to listen real close. This is a fast one.
Is the universe expanding into itself?
Okay. Did you catch that?
Yeah, I did.
Is the universe expanding into itself?
What?
My only guess is that was an Australian. I heard that. Yeah, it was an Australian accent, but we don't know who or where. But thanks for the question. It is one of the theories, isn't it?
Well, yeah. I mean, it's the normal definition of the universe is everything that we can observe or see. But that's been kind of overcome, because if we could observe other universes, then it's not a universe. So I think it's possible that the universe may be expanding into itself if you postulate that our universe includes higher dimensions that we can't yet detect. So if you think of the universe sitting in a 5-dimensional space, which by the original definition of universe must belong to the universe is expanding into that 5th-dimensional space, then maybe it is expanding into itself. But it's a question that we can't really answer. All we can measure is that the universe is expanding, because we can see the different distance between galaxies increasing. And we know that it has done because of things like the fact that the flash of the Big Bang, which we can still see, is not brilliantly visible light. It's redshifted to be microwaves because of the expansion of the universe. So there's plenty of evidence that the universe is expanding, but that's all we can measure. We can't say, all right, does the universe have an edge? Is it expanding into something else? There's no observations we can make that would physically let us detect that. Some people think that if you look closely at the temperature fluctuations in the cosmic microwave background radiation, the flash of the Big Bang, then you might see evidence of other universes. And in fact, I think Roger Penrose authored a paper a few years ago that postulated that, because he saw what he thought was a circular feature in the pattern of slightly higher and slightly lower temperature regions in the cosmic microwave background radiation. But I don't think many people believed it. So I think it was very controversial. What the universe is expanding into is as yet an unknown question. So maybe it is expanding into itself, and maybe not.
There you go. We've lived up to our reputation of not being able to answer your question.
But that's because nobody knows, not because
nobody knows. No, that's very true. Yes, good clarification. That. Yeah. Thank you for the question, though. It's certainly a fairly common topic which a lot of people speculate about. So good to get the question. This question comes from Rachel in South Yorkshire. Hi, Andrew and Fred. I love your podcast and finally plucked up the courage to send you a question. Oh, thank you. What is the Booty's void? Is it related to dark energy or dark matter? And is it expanding? Could you see other galaxies if you were in it? Thanks, Rachel. Good question. We have talked about the Booty's void before, but not for a while.
That's right. We have. It's usually called the Boaty's void.
Is it? I knew I got that wrong, but I thought I'll just stick to my guns.
You've got to, Andrew. All I'm saying is booty sounds like something you buy for,
for a baby.
Yeah. Whereas Bootes is, if I remember, it's the charioteer, isn't it?
Bootes, yeah. I don't know.
Yeah, I think it's a constellation.
Our little granddaughter, Felicity, is just starting to get her mouth around words, and she's learned how to say shoes and socks, but it comes out as shoo for shoes, for socks. It's so cute.
It's very cute. Yeah, yeah.
And she can't say bird, but she says buck, buck, because they got chickens. So that's a bird.
That's good.
Kids are amazing.
They are indeed. Yeah, I'll refrain from telling you what all my kids call different things, but they were very entertaining.
It is entertaining. I love it.
The what? Just mention one. My eldest son James, when first introduced to a helicopter, called it hopper-dopper-dopper. Because that's the kind of noise it made.
That's really good. I like it.
It's neat, isn't it? And because they do hop as well. Anyway, I don't know. It's very young. Okay, but back to the Bootes Void, or the Bootes Void, sometimes known as the Great Nothing. I love that. Yeah. So it's a region of space in the direction of the constellation Bootes, and it's got very few galaxies in it. Which is why it's called a void. It's very, very large, with a radius of 62 megaparsecs. Now, a parsec is 3.23, is it million? Sorry, 3.23 light years. So that's 62 times 3.23 million light years. That is very big. In the region of 500, 600 million, something more like that. Wait a minute, let me do that sum again. That's the diameter rather than the radius there. So you're talking about a huge void in space. Now, voids in space without galaxies typically are about 100 million light years. So we're talking about something much bigger than that, of the order of 3 or 4 times bigger. So that makes it unusual, and the usual reason for voids, this, and Rachel's put a finger on this, is the cosmic web. This honeycomb of, basically we see them as galaxies, clusters of galaxies, strings of galaxies, filaments of galaxies, which define this structure, which has empty spaces in the middle, the cosmic web, and typically those honeycomb voids are about 100 million light years across. So the Bootes void is bigger, and I'm not sure whether anybody understands the reasons for that. Here's a one thrown into the mix, once again from our old friend Wikipedia. It's been theorized that the Bootes void was formed from the merging of smaller voids, much like the way in which soap bubbles coalesce to form larger bubbles. There you are. That would account for the small number of galaxies that populate a roughly tube-shaped region running through the middle of the void. So, yeah, a really interesting thing. The dark matter connection, Andrew, is that we think that the structure of the cosmic web was laid down in the very early history of the universe by strings of dark matter, and they formed a kind of gravitational nucleus for strings of galaxies to form around them, because they pulled hydrogen in, hydrogen being the raw material of galaxies and stars. So there is definitely a link there. Perhaps less obviously with dark energy, though, because as I said a few minutes ago, we think dark energy is constant throughout the universe, whereas dark matter definitely isn't. It's blobbing about everywhere.
Okay. Thank you, Rachel, and great that you finally plucked up the courage. I didn't think we were that scary, but appreciate the question about the Bootes void. And finally, a bit of a speculator from Robert.
Hello, Fred and Andrew. It's Robert from the Netherlands. I never miss an episode from you guys. I always love listening to the podcast. Thank you for making it. I have got a little thought experiment for you. Let's consider for a second that the space travel is so fast you can go anywhere you want instantly. And you guys are going to have to start a new colony for humanity. what location would you choose? Would it be Jupiter or Mars, or maybe a distant galaxy, or would it be low gravity, something with a Wolf-Rayet star, or like black hole, or something very quiet? What sort of items would you bring? And would you bring the wife? Love to hear the answer. Thank you so much. Take care.
Would you take the wife? Not going there.
I think, Robert, we might draw the line at going there, because naturally we will both be taken by our respective partners.
And I don't think I'd get to decide.
No, that's right. No, quite right too. Absolutely right.
So you could go anywhere you liked instantaneously.
Yeah, I do like. Go? Well, that kind of, if you can do that,
defeats the purpose, really.
What it means is that you could, having sifted through the 5,000 known exoplanets that we now know exist around the sun's vicinity in our galaxy. And there are probably many more, because we think every star has probably at least one planet. So what you do is you sift through all that and pick out the most Earth-like one that you can find.
Exactly what I'm thinking.
And you go there.
Yeah. Aren't there a couple in the Kepler system?
Yeah, there's a few. There are a few candidates. There's nothing that you could describe perfectly as Earth 101 or Earth version 2.
Earth 2.
Earth 2, that's right, 2.0. Earth 101 might be a bit further down the track. But yes, we do see evidence that there are some Earth-like planets. I don't think any of them, though, have been discovered at the same distance from a normal star as we are from the sun. So we're still sort of looking. But pretty well anywhere else in the universe, to start a colony, and that's not an idea I'm very fond of anyway, but pretty well anywhere else is awful. It's just not somewhere that humans would want to be. The nearest thing in the solar system, the nearest what you might call benign place, would be the planet Mars.
Yep.
It's arguable that Mars is less benign than the Moon, though. Even though the Moon has no atmosphere, Mars has a bit of an atmosphere, but not enough to make it worthwhile. It's only 0.6% of the atmospheric pressure of Earth, and it's mostly carbon dioxide anyway. So you can't really do much with that. The Moon has less of an atmosphere, but it's nearer to the sun, so you get more solar energy on the Moon. Yeah, and those are the only two places that you could really think about putting large numbers of humans down. Yeah. Once you get out to, Venus, too high in atmospheric pressure, too hot. Titan, atmospheric pressure again is high, too cold. Horrible atmosphere, again, carbon dioxide less with methane and ethane.
And don't drink the water.
Don't drink the water because it's natural gas, liquefied natural gas. Oh, dear. Yeah, we are so finely tuned to a planet like ours that it really isn't worth looking for anything else other than Earth version 2.
Yeah, which they are looking for. They just haven't found one. They've had a couple of close calls, but the planets are much larger than Earth, and so even if you could go there and it had trees and lakes and fish, the gravity would be a problem.
Yep. Yeah, that's right. There's all of that.
Yeah. So, and the life on it, let's say you found an Earth-like planet that was double the size of this one.
Yeah.
And it had animal life, like it would be very inhospitable to us because we would be so out of tune with the reality of it, and So if we did, though, would over time we, as human beings, be able to adapt?
Well, evolution kind of still going on, but you're talking about a very long time there. Yeah. So my real answer to Robert would be, you stay not very far from Earth and you build a megastructure. Which I think is, if you've got the scientific ability to go anywhere instantaneously, you're not going to bat an eyelid at building a halo world, one where you've got artificial rotation.
Oh, that's a good idea.
Provides gravity and that holds onto an atmosphere and all of the above. Beloved of many science fiction authors.
You could go and park that out near the James Webb Telescope.
Yeah, wherever you feel like it. That's right. Yeah. And
that would be a good spot. You calm waters out there.
Well, there would be if you built your own oceans as well. Do all that.
Yes, indeed. I saw a story the other day about a bloke who's built an underground silo for the end of the world, and it's multi-level. It's like from that TV series Silo. He's built something like that.
Okay,
quite bizarre, but in space, why not? It'll happen one day. You know that, Fred, don't you?
I do. I hope it will.
Yeah. All right, Robert, thank you. My choice would be Mars, just in case you're wondering. And yes, I would take the wife because she loves cold weather. I've got to find a way to stay warm somehow. Thanks, Robert. Thanks to everyone who sent in questions. Much appreciated. Don't forget, if you have questions for us, we would love to hear from you. Just go to our website and send us the question through the AMA tab or the send us your voice message tab on the right-hand side. As long as you've got a device with a microphone, you're all set. And don't forget to tell us who you are and where you're from, because we love to know. And welcome aboard to those newbies who sent in questions for this particular episode. Much appreciated. And thank you, Fred, as always, for filling in the blanks for us and creating more.
Yes. Yeah, in a state of total confusion.
That's the way we love to live on Space Nuts. All right, Fred, thanks so much. We'll catch you next time.
Sounds great, Andrew. Take care.
See ya. Fred Watson, astronomer at large, and thanks to Hugh in the studio for turning up today and doing the usual. Yep, that's it. There, nothing. And from me, Andrew Dunkley, as always, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.